Good day, everyone, and welcome to another problem solving session with Special Maths Academy. So we'll be discussing the just concluded second round of the Nigerian Mathematics Olympiad. So we're looking at the senior category. So this is problem 1. So it says if X, Y, and Z are the lengths of a side, a shortest diagonal and the longest diagonal, respectively, of a regular nonagon, write a correct equation consisting of the three lengths. Okay, so one of the things we'll be using is the fact that all regular polygons are cyclic. And then just for convenience, although you don't have to, we're using Ptolemy's theorem. Okay. So let's start with the fact that all regular polygons are cyclic, and let's see if we can just prove that at least for the nonagon and see where that leads us. Okay. Okay. So we just have a quick sketch of a nonagon. So let's try and prove this, that all regular polygons are cyclic. Okay. So first of all, we know that every triangle, so I'll be highlighting very important information. A triangle defines a unique circle. So a triangle has a unique circle passing through its three vertices. So let's label this nonagon. So I'll just start by point A, B, C, D, E, F, G, H, I. Okay. Now, let's start by just talking about the circle of the triangle ABC. So we start from the circumcircle of triangle ABC, and then we try and show that that circle is also the circumcircle of the nonagon. So we start from the circumcircle of triangle ABC. Okay. Now, so I'll just draw this diagonal first of all. Okay. So let me just draw this diagonal. So sorry about that. And we bring in the triangle BCD. Okay. So triangle BCD is brought in. Bring in. Okay. Now, another thing which is worth taking note of is that we're starting from the definition of a regular polygon. So I'll just put here what definition of a regular polygon are we going to use to show that a regular polygon is cyclic, at least in the case of the nonagon here. So I'll just write it here. So a regular polygon, very important, has all sides and angles equal. So it must have all sides and angles equal. Okay. So now we have, so I'll just mark it that all sides are equal. And then all the angles are equal. Okay. So we have this angle here is equal to this angle here. And so we can look at triangle ABC and triangle BCD. And what do we have? So for triangle ABC and triangle BCD, we have that side length AB is equal to side length BC, and we have that side length BC is equal to side length CD, and then we have that the angle, because all angles of the regular polygon are equal, so the angle ABC is equal to the angle BCD. So by side angle side, these two triangles are congruent. And if these two triangles are congruent, then it means all their respective angles are equal. So let's just break that in. So it means that this angle here is equal to this angle. But since it's isosceles, these angles are equal, so it's also equal to this angle. And then we also have that this angle is also equal to this angle. So in fact, these four angles I've shaded are equal. But what's our point of concern here? What's our point of interest? Our point of interest are the two angles I've left shaded. Now, what does this tell us? This tells us that ABCD is acyclic quadrilateral. Okay, once you have a chord sustaining equal angles, we have a cyclic quadrilateral, and we can see that here. Since angle since angle BAC is equal to angle BDC, so the chord BC rather, the chord BC is subtending an equal angle. Okay, so I have ABCD is a cyclic quadrilateral. So what do we have? So it means in the second circle of triangle ABC, so I'll just use a bracket to denote circle. So we're talking of the circle of triangle ABC. We have that D lies on that circle. So D is a member of this circle. Okay, and we can keep on going like that, and we keep on adding circles, because we can add this point here. So we can keep on adding points to that circle. We see that E is also a member of that circle, and so on and so forth. Okay. So we can inductively keep on adding points to the circle. So when we go that ABCD, the circle ABCD, we have that E is a member of the circle ABCD. And so you get the idea, yeah? You get the idea, and we can add all the points in the circle. But this is it's a well-known fact, and something that you don't have to prove in an exam condition. So I'll leave that to you, the viewers, to convince yourself and get a rigorous proof that all regular polygons are cyclic. So we just kind of gave a sketch of why that should be true for a nonagon. Okay, so I'll erase all this. Sorry about my cough. I'm feeling good, and it's nothing serious. Okay. So I have to erase this quickly. Okay, so yeah. I'll just erase this, since we know it's a regular nonagon. I don't need all this. So I'm trying to make my diagram as neat as possible. So I'll just erase this, and then I'll mark the first point. I'll mark the first point as done. Okay. Now, how can we apply Ptolemy's theorem? Okay, so we're told that this is point X, and okay, so one of the things we can do, let's look at this. So now we have that this is a circle, right? And one of the things we can do is to we can form an equilateral triangle. And soon we're going to see why this is an equilateral triangle. So we can form an equilateral triangle And that's because the angle at the center for each of the chords, so that is AD, DG, and GA. The angle at center is that each of the chord substance are all equal, and so we can quickly get the angle at the center. So each chord of this, each side length of this non-argon substance an angle of 360/9, since they are all equal, and at the center, and this is going to be equal to 40 degrees. So we have 40 times 3, so this whole angle here is going to be 120. So it means if we raise all this, well, that this angle here is 120 degrees. And we can get the same thing for each of the other sides. And we can see that these are all equal chords, okay? So we can erase this. So we have that this is an equilateral triangle. So very important note, triangle ADG is equilateral. Okay, so one of the quick things we can do, now we want the longest diagonal, okay? So now the longest diagonal, so which is Z, so let's just look at what we're talking about. We're trying to focus on Z now. So the longest diagonal will divide the non-argon, into to cut between 4 sides and 5 sides in any either way. So we can just bring in BG. So BG is one of the longest, diagonal. Okay, so BG. So I'll just put this is side length of Z. The length of the side of the non-argon is X. Okay, and then shortest diagonal, just cutting out 2 sides. Okay, so this is going to be Y. Okay, so I'll just use a red color to highlight the cyclic collateral I'm centering on. Okay, so look well at this cyclic collateral. Okay, so let's call the side of the equilateral triangle, let's call it S. So this S. Now Ptolemy's theorem needs to come into play here. So what does Ptolemy's theorem state? So you say that if you have a cyclic collateral, okay, so if you have a cyclic collateral A, B, C, D, the sum of the product of the opposite sides, so AB times CD plus AD times BC is equal to the product of the diagonals, so that's AC times BD. Okay, so let's apply this now to the quadrilateral A, B, D, G. Okay, so let's apply Ptolemy's theorem to this quadrilateral. So let me just put it down here. So quadrilateral A, B, D, G in this case. So from Ptolemy's theorem, what does this give us? We have product of opposite sides. So we have S times Y, so SY, so we have SY, and then XS, so SY plus XS, and then product of the diagonal of the cyclic collateral, so S times Z. So we can divide through by S and we get that X plus Y is equal to Z. So this is one of the best possible equations you can get. And one thing you should take note of is that there are many possible equations you can get, as you'll see. So I'm going to just derive 2 so that this video will not be so long. So one of the best solutions that you can get, one of the best equations you can get relating the side lengths X, Y, and Z is that X plus Y is equal to Z. Okay, so let me scroll down a bit. Okay, cool. So let's try and get another question, or let me just so let me just leave that written so that you can always look at it as I'm going to the next part. So let's derive the other equation. let's derive another equation. So as to just convince us all that so as convince us all that we can get more than one equation, that can get as many equations as possible. So let's just get another equation. Okay. So let's bring in this. So now we want to relate x, y, and z. So this other method I'm going to do now, it's not as elegant, but it's going to involve us applying Ptolemy's theorem twice. So for instance, we have this is x, this is x, this is x, this is y. And this is y. Okay, and this is s. So applying Ptolemy's theorem to this quadrilateral. So applying Ptolemy's theorem to the quadrilateral A, G, H, I. This will give us a way of relating x, y, and s, but what we want is z, not s. But first of all, let's just get with s, okay? So this will give us what? X times s, so some product of opposite sides, x times s plus x times x, so that's x squared is equal to y squared, okay? So this gives us x times s is equal to y squared minus x squared, which implies, so we're finding a way to remove s, so we want to make s such a formula, and so this implies s is equals to y squared minus x squared all over x, okay? Okay. Now let's find a way to relate s to z and maybe either x or y, okay? So let's bring this in. Okay, so this is z, okay? And this is x again. So let's look at the cyclic quadrilateral A, B, G, H. Okay, what does this give us? So I'll just erase this so as to prevent the distraction. So we have this is S. This is also going to be S. I can say this, quickly because this is a cyclic quadrilateral. This is cyclic quadrilateral, and so these two triangles are going to be congruent because this angle here is going to be equal to this angle. Okay, and since this side here is already equal to this side, and this base here is shared. Okay, and also yeah, and since this base here is shared, we can quickly get that these two triangles are congruent, and so that's how we just get that the diagonals are equal. And another thing you can take note of is once you have a cyclic quadrilateral, once you have opposite sides of a cyclic quadrilateral being equal, you will get an isosceles trapezium. And an isosceles trapezium is no cyclic here. So one of those things that you just want to have at the back of your mind. Okay. So ABGH. So to get ABGH, to be to relate the sides and diagonals of ABGH using Ptolemy, so we can quickly get YZ plus x squared equals to diagonal, product of diagonal, so s squared. So this implies that we can put what we have for s, which is this, we can put it in this equation and we get yz plus x squared all over, rather, not all over, so it's equal to y squared minus x squared all over x all squared. And although this is much more complex because this is a fourth degree equation, but I mean they just asked for an equation relating the sides. And so that's it. So for as a challenge to the viewers, I want you guys, to get more equations. Try and get maybe 2 more equations relating X, Y, and Z. And that'll be all for this video. So see you guys in the next video. Goodbye, guys.